Hello, my name is Samuel Schlafer, and this is my Physics 2211 Lab 5, Choose Your Own Adventure. And for this lab, I chose to do the energy conservation principle using a previous lab tracker video for Lab 2. Little introduction to this lab. The purpose of this lab was to demonstrate changes in potential, kinetic, and total energy of a system in which we have a mass in projectile motion. In order to create the experimental model, I used the tracker app, and in order to create the computational model, I used GlowScript code. Some fundamental principles behind this lab. First off, we have change in gravitational potential energy, in which we have delta U equals mass of the object times gravity times the change in heights. We also have change in kinetic energy, which equals 1/2 times the mass of the object times the final velocity squared minus the initial velocity squared. And then finally, we have the change in total energy. For this lab, we are expecting that total energy should remain about the same, showing a flat or horizontal line on a graph over time. Meanwhile, as gravitational would increase, we would expect kinetic energy to decrease and vice versa. So here's the experimental model. Like I said, the mass of the paper ball we used was around 0.0045 kilograms. I set the initial position to 0, 0, 0 and calculated the initial velocity to be about 1 meter per second in the x and 2.8 meters per second in the y. On the right side of the slide, you see the change in x over time for the object, and in the bottom right, you see the change in y over time for the object, and on the left, you see the actual video. Here are the results from the experiment. So on the left, we have kinetic energy versus time, and we see that it starts with very high kinetic energy, and as it reaches the peak at around 3.9 seconds into the video, it reaches its minimum of 0 kinetic energy, where it then begins to increase again. And for the gravitational potential energy graph, we see that it does the opposite. And although it doesn't look quite right for the total energy graph, we see that it remains kind of horizontal. It starts off a bit high, and I will go into reasons later as to why there might be some error. But for the most part, the principle of as kinetic energy increases, gravitational potential energy decreases, that principle is shown to be true. So here's the computational model and some of the code I used for it. I input the same initial conditions. On the left, you see the first half of the simulation loop. And the right, you see the time update part of the simulation loop, as well as showing arrows and energies for the mass. Here are the computational results. So a lot more ideal and a lot more of what you'd be expecting to see. So on the left, you see kinetic energy increase over time. On the right, you see gravitational potential energy decrease over time. And then overall, the total energy for the system should decrease in a linear fashion as it reaches 0. Some potential causes for these differences are outside forces, rounding error, and then human error. In the real world, there is more than just the applied force. There's also friction and air resistance to worry about, which could cause for lesser numbers than what the computational model was providing. As always, there might be rounding error in between the two models. And then for the human error, I plotted the point where I believe the center of mass was for the object at each frame. And since I wasn't doing anything scientific to compute where that point was and only eyeballing, there could easily be some error in it. And that is all for this Lab 5 Physics 1 presentation.